Section 1 Introduction. We're going to talk about large language models, LLMs, which are becoming increasingly important in many applications that need to understand and process natural language. One of the reasons why these models are so popular is because they can be fine-tuned, or adjusted, to perform specific tasks very efficiently. This means we can create specialized models that are really good at certain tasks, even if we don't have a lot of data to train them with. However, fine-tuning these models can be quite resource-intensive, especially when dealing with large models that have billions of parameters. Moreover, it's often necessary to maintain different versions of the model for different users and tasks, which can be quite costly as the number of users and tasks increase. Therefore, it's crucial to use the model's parameters as efficiently as possible. One method that has gained popularity for its efficiency is low-rank adaptation, LoRA. It's easy to implement and allows us to incorporate the LoRA weights into the base model. But LoRA training can still be expensive, especially for larger base models. Previous attempts to make LoRA more efficient have focused on selecting the right low rank. However, we're proposing a new approach. Instead of controlling the number of parameters by the rank, we're going to use a simple weight tying method combined with selective training. We've come up with several configurations of this Tied-LoRA method and tested them on 5 different tasks. Our work has 3 main contributions. 1. We've proposed several configurations of Tied-LoRA that use simple weight tying and selective training to make LoRA more efficient. 2. We've tested these configurations on a variety of tasks that represent real-world problems. 3. Based on our tests, we recommend a specific configuration that maintains performance while reducing the number of parameters by about 87%. Now, let's talk about some related work. Recent studies have shown that fine-tuning pre-trained language models in a parameter-efficient way can yield competitive results, often matching the performance of full fine-tuning for task-specific customization, but with fewer trainable parameters. One popular method for this is LoRA, which uses low-rank matrix approximations of full weights gradient descent update to significantly reduce the number of trainable parameters. Importantly, LoRA can incorporate these low-rank updates into the base weights after the fine-tuning process, without any changes to the model's architecture or inference speed penalties. Since LoRA was introduced, there have been several attempts to improve it. Most of these efforts have focused on reducing the number of trainable parameters and memory footprint while increasing the method's performance on downstream tasks. For example, Tied-LoRA introduces dynamic rank adjustment for the low-rank matrices during the fine-tuning process. Another method, VERA, freezes randomly initialized projection matrices and introduces trainable scaling vectors that vary across layers. This method shows similar performance to LoRA while significantly reducing the number of trainable parameters. Our work is heavily inspired by the principles of the VERA method. Another related work, QLORA, significantly reduces the memory usage of LoRA by using a 4-bit or 8-bit quantized base language model during training. Combining quantization and reduction in the number of trainable parameters is a promising direction for future work. Section Summary. Large language models, LLMs, are widely used in natural language processing, NLP, tasks, and fine-tuning pre-trained LLMs for specific tasks is a popular approach. However, fine-tuning can be computationally expensive, especially for large models. To address this, we propose Tied-LoRA, a parameter-efficient fine-tuning method that combines weight tying and selective training. Our study shows that Tied-LoRA configurations can significantly reduce parameters while maintaining performance. Additionally, we discuss related work on parameter-efficient fine-tuning, low-rank adaptation, LoRA, and extensions to LoRA such as Tied-LoRA, VERA, and QLORA. Section. Weight tying. In this study, we're exploring a technique known as weight tying. This method is often used to decrease the number of parameters in a model by using the same set of weights for both the input and output word embedding layers. We've applied this technique to the low-rank weight matrices used in a method called LoRA, and we've shared these weights across the layers of the base language model. This simple step leads to more efficient training methods where the number of trainable parameters either remains the same or only increases slightly with the number of hidden layers. As models become deeper, this approach naturally results in a greater reduction of parameters compared to the original LoRA method. In this section, we're introducing a generalized approach for fine-tuning large language models in a parameter-efficient way through low-rank weight update approximations. This approach, which we call Tied-LoRA, offers a variety of training strategies through a series of design choices over selective parameter training and weight tying. We use weight tying along with pairs of projection matrices and scaling vectors that can be selectively either trained or frozen. Since the low-rank computation path doesn't introduce any nonlinearity, all Tied-LoRA configurations can be merged into the base model weights to prevent additional latency during inference. The overall structure of the Tied-LoRA framework can be seen in the figure. The original LoRA uses a dedicated pair of low-rank projections for each of the Q, K, V matrices. However, in our formulation, W is a matrix that jointly projects Q, K, and V attention matrices, where D is the hidden size of the base language model. Our down projection A is a matrix of shape D by R, and up projection matrix B has shape R by 3D, where R is the low-rank bottleneck dimension. Essentially, the down projection A is shared by Q, K, and V, leading to fewer trainable parameters than the original LoRA. For a linear layer with a frozen pre-trained weight matrix W, we define the layer output as Z equals Wx plus a scaled version of the low-rank approximation to the parameter update matrix. Unlike the original LoRA, where the scaling factor is a hyperparameter that can be manually set, we simply set the scaling factor equal to R, effectively removing its scaling effect. This equation is a generalized formulation for methods that utilize low-rank approximations to estimate parameter updates. Particular settings of parameter updates and weight tying reduces this equation to some of the existing formulations in the literature. Weight tying is a critical ingredient of our proposed approach, which drastically reduces the number of trainable parameters. For example, training using the 7B Llama 2 language model with a typical low-rank setting of 8 requires about 4.2 million trainable parameters. By merely introducing weight tying across the 32 layers of this model reduces the trainable parameters to about 131,000, which is a 96.875% reduction. In comparison, the Vera method results in a reduction of 90.6%. Section Summary. Weight tying is a technique that reduces the number of parameters in a language model by using the same set of weights for both the input and output word embedding layers. In this study, weight tying is applied to the low-rank weight matrices used in LoRA, resulting in efficient training methods with minimal increase in trainable parameters as the model gets deeper. By introducing weight tying across the layers of a 7B Llama 2 language model, the number of trainable parameters is reduced by 96.875%. Section 3.3 Selective Training. In Section 3.3, we discuss selective training. The equation we're working with provides a flexible framework that allows us to explore a range of training configurations. By selectively updating the components A, B, U, and V during the training process, we can create a variety of methodological variations. These variations not only differ in the number of parameters, but they also show different capabilities across various tasks. This exploration lets us delve into the fascinating area of extremely low parameter and low-rank PEFT models. This is a crucial step towards customizing models, allowing them to excel at specific tasks while keeping the number of parameters to a minimum. Our ultimate goal is to leverage this methodology to create highly efficient, task-specific models that deliver high performance with reduced complexity. In Section 4, we evaluate the different configurations possible within our Tied-LoRA paradigm. While both LoRA and PEFT methods can be used to train models for general instruction following, we focus our evaluations on a task customization perspective. Here, each model is trained on a specific task and is evaluated on a test set from the same task. In Section 4.1, we discuss the tasks and datasets we used. Extractive QA is a common task where the model is expected to read some relevant text and answer questions. The answers are usually exact substrings from the provided context. We use the SQUADV1 dataset in our experiments. Since the official test split of this dataset does not contain ground truth answers, we use the validation set as our test set. We create a validation set comprising of a random sample of 4,800 examples extracted from the training set. Summarization is a central problem in NLP, and several variations of summarization datasets have been proposed. We use the dialog sum dataset to study our model's performance on this task. Dialog sum includes summaries of real-world conversations on a diverse set of topics and scenarios. This dataset was an attractive option as the length of the conversations and summaries are within the context lengths of the base language models. Common Sense Natural Language Inference, NLI, is a task designed to probe the ability of language models to apply common sense reasoning to choose a possible ending for a given situation described in natural language. These tasks are typically easy for humans, but language models can still struggle. We use the HELA-SWAG dataset to study the performance of our proposed models on this type of task. As HELA-SWAG contains multiple choice questions, it can be viewed as a classification problem. Translation is a natural language generation task which is widely used in research and industry. Translation is inherently multilingual and thus offers a challenging domain to study our Tied-LoRA paradigm. We focus on a moderately sized IWSLT 2017 German to English translation dataset. The dataset contains translation of spoken language into various other natural languages. With over 206K training examples, this is the largest dataset that we study. Mathematical reasoning is a challenging domain where large language models still lag behind human performance. Using PEFT methods on such tasks further amplifies these challenges as there are very few trainable parameters. In our experiments, we use the GSM-8K benchmark, which contains 8.5K high-quality, grade school-level math word problems. Each example in the GSM-8K benchmark contains a question and an answer. The answers are provided with natural language solutions which contain explanations of each step used to obtain the final answer. The final numerical answer is demarcated from the rest of the natural language solution. We evaluate our models by comparing these final numerical answers. In section 4.2, we discuss the base language models. Although PEFT enables the base language model to perform new tasks, the final performance heavily depends on the inherent abilities learned during pre-training. This necessitates investigating the performance of Tied-LoRA on multiple base models with different inherent capabilities. Therefore, we use a relatively small 2 billion parameter, GPT-2B001 model released by NVIDIA and the moderately large 7B Llama 2 model released by Meta. In addition to the size differences, these models also differ in the amount of pre-training data used. The GPT-2B001 model was trained on 1.1 trillion tokens of text from publicly available multilingual text spanning 53 languages. The Llama 2 7B model was trained on 2 trillion tokens of predominantly English text. Both models are auto-regressive language models with a context size of 4096 tokens. Section Summary. Selective training allows for the exploration of different training configurations by updating specific components during the training process, resulting in variations in parameter count and capabilities across tasks. This approach aims to create highly efficient, task-specific models with reduced complexity. The experiments focus on evaluating different configurations within the Tied-LoRA paradigm, with a specific emphasis on task customization and performance evaluation on various tasks such as extractive QA, summarization, common sense natural language inference, translation, and mathematical reasoning. The performance of the models heavily depends on the inherent abilities learned during pre-training, which is why multiple base language models with different capabilities are used. Section 4.3 Implementation Details. In this section, we'll discuss the specifics of how we implemented the algorithms we've presented in this paper. We used the open-source NeMo framework for this purpose, and our implementation is publicly accessible via the NeMo GitHub repository. We ran all training routines for a maximum of 2,000 steps, but we often stopped training earlier to prevent overfitting. This early stopping was done with a patience of 10. We used the AtomW optimizer for training all configurations, with a weight decay of 0.01. We also used a cosine learning rate schedule with 50 warm-up steps. For each Tied-LoRA method, we experimented with two learning rates, a high rate of 0.0001 and a low rate of 0.00001. We found that some complex tasks benefited from a higher low-rank dimension, so we trained our models with a range of low-rank dimensions from 2 to 128. Each task was trained with a global batch size of 256 and a validation check interval of 30 steps. The only exception was the IWSLT translation dataset, for which we used a global batch size of 1024 and a validation check interval of 60. We didn't conduct an extensive hyperparameter search. During the inference phase, we used greedy decoding to generate the model's predictions, with a limit of 500 tokens. Now, let's discuss the results. We found that the LoRa model performed the best for both the 2B and 7B base language models. This wasn't surprising, as LoRa is the most resource-intensive method that doesn't use tied weights. The next best performing method was FA-chain, which had average scores comparable to LoRa, demonstrating the effectiveness of weight tying. However, FA-chain didn't perform as well when the scaling vectors were increased, especially when the rank was increased to 128. The third best Tied-LoRa configuration was FA-chain, which outperformed other Tied-LoRa methods that used more parameters. Interestingly, Vera, which uses fewer parameters than FA-chain, had better performance. FA-chain performed the worst in most cases, especially when the rank was increased. When we looked at the performance for each task individually, we found that for tasks like Hella Swag and Squad, Tied-LoRa methods, specifically FA-chain and LoRa, performed almost the same over the entire range of ranks, but with fewer parameters. For example, FA-chain only used 4.2% and 3.1% of the parameters that LoRa used.